In this video, I'll be discussing the same situation from part 1, only now we need to consider that after a minute and 40 seconds, or 200 seconds total, the flow to the first tank is reduced to 80% of its initial steady state value. And then again at 3 minutes and 20 seconds, so 200 seconds total, the flow to the second tank is increased by 250% its initial steady state value. So to analyze this change in the system using the differential equations we derived in part 1, I'll be writing some code in Google Colaboratory to solve differential equations with this information. So I already have all of these initial inputs. So we have SciPy and JAX, Plotly, and this just allows us to perform numerical differentiation and to be able to generate plots. And then I also have listed below that all of our data that we got in the last video, just giving measurements such as the cross-sectional area of both pipes, which is A12 and A2, which are both 0.2 meters squared, the initial heights of the fluid in each tank, which are H1I and H2I, which are 5 meters and 3 meters respectively. Then we have the radius of both tanks. And I also put in a shortcut for the square root of 2 times gravity, since that pops up in a lot of our equations. And the T end value is the final time, which is 200 seconds. So the first thing that we're going to do is solve for the cross-sectional area of each tank using equations that we found in part 1. So the cross-sectional area for the first tank is going to be pi times the radius squared minus the initial height minus the radius squared. And then we can do the same thing for the second tank. So now we have the cross-sectional area of both tanks. So now we want to add in expressions for the initial steady state flow rate that we found in part 1. So Q12 and Q1. Which again, we said was the cross-sectional area times of the pipe times the velocity of the fluid moving through that pipe. And in part 1, we derived an equation for that velocity. So J and P sine of the initial height 1 minus the initial height 2 is going to give us that sign that that's not accounted for because of the square root. Again, we did that in part 1. And then we have our shortcut for the square root of 2 times gravity. And then we multiply that times the square root of the difference of our heights. Okay, so we can do the same thing for the second tank. The second pipe, I should say. We just had the square root of 2 times gravity times the second initial height. Okay, so now we have those flow rates. So to condense the graphs that we're going to end up with, so the functions that we derive, we want to condense them into a sigmoid function so that the values are between 0 and 1. And we can turn it into a stepwise function so we can see exactly what we're looking for. And with a sigmoid function and just rules of equations when graphed, it can be horizontally translated, vertically stretched, vertically translated, and compressed or expanded. And well, the way that we're going to do this is we're going to have it be horizontally translated by t switch, which is the difference in time, vertically stretched by the difference between the final and initial velocity, vertically translated by the initial velocity, and then we'll compress it by an arbitrary scale, which I'm going to pick to be 0.01 because that's what gives us a stepwise function. So we can define switch with time, initial velocity, and velocity, and switch, and scale. And we want to return the sigmoid function. So we want it to be time minus time switch divided by the scale, and then multiplied by the velocity difference plus the initial velocity. Okay, so we can go ahead and give that function values for both tanks. And so then for tank 1, define it as n of t. We want to return that function. And since our first tank, the change in volume is going to be decreased down to 80% its initial, we have 0.8 times the input initial flow rate. And then again, 100 for 100 seconds and 0.01 for the scale to make it a stepwise. And then, so for the flow rate going into tank one, the initial velocity is the initial flow rate in, the final velocity is the initial flow rate in times 0.0 or 0.8. So that's what we have here. And then the time difference is 100 seconds again, and we choose that scale. So then we can do the same thing. We can do the same thing for the second tank. And this one increased by 250%, so we will multiply it by 2.5. Again, that's that initial flow rate, which will multiplied by 2.5 gives us our final velocity. And the total time for the second tank was 200 seconds. And again, we're using 0.01 as the scale. So now we want to insert differential equations found in part one for the flow rates with change in height with respect to time. So that was the right-hand side of our equation. So we want to define dH over dt, which is the change in height with respect to time of T and H. And to make it the most similar to what we would do in real life and what we did in part one, we are going to give H1 and H2 values like this. So H1 will be indexed at 0 and H2 will be indexed at 1. And this just makes everything cleaner. So then for our flow rate of the pipe between tank 1 and 2, we have that cross-sectional area. Times the sine, not counted for in the square root, multiplied by our shortcut for the square root of 2 times gravity. Times the square root of the absolute value of the height difference. And we can do the same thing for Q2. And then we want it to return an array. These are, again, the steady state equations that we found in part 1, which gave us the flow rates, the total flow rates. So it was the flow rates divided by the cross-sectional area of the tanks. So it was the difference in flow rate. So once again, this last column that I have per row written are the differential equations we found in part 1 for the flow rates with the change in height with respect to time. So now we want to solve the initial value problem for the total time interval, which was again 200 seconds. So solve initial value problem. UHDT, just what we just put in. From 0 to 200 seconds, which again was our T end value. With our two initial heights. So we also want to plot it. So we can define T plot. We want to take it from 0 to 201 instead of 200, which will plot the height from 0 to 201 seconds. And if we were to look at the array, we would see that the SOL value is the value that we want because this gives height values that we want. So the SOL index at 0 is the tank 1 height, and the SOL value index at 1 is the tank 2 height. So shift enter. Height So messed up period here. Fix it. Okay, so had to do some debugging. Now we're good to go. And all we have left now is we just need to plot it out and then we're done. And also just a note on what I had to do. It was just variable error, typing in the wrong things as variable names because things get really similar when you have all these different initial values and whatnot. So figure it out now and we're in the long stretch. So we can just copy and paste this other one because it's basically just the same thing, but we want to have two plots for each one. We can copy and paste that and then just change this to index 1 because that's our second height. So for here, we have a second graph showing us those flow rates. So that gets put into column 2. And again, we can just copy and paste that. Second one. Okay, so we have 4 different lines and 2 different graphs. So on one graph, we'll have the change in height, and on one graph, we'll have the change in flow rate, and it should look like a stepwise sigmoid function. And there we go. So we now have 2 plots, one showing the height of both tanks with respect to time, and one showing the flow rate of both tanks with respect to time. So, yeah, thank you for watching.